Right, so to solve this one, we used substitution, and that means we did what? Multiplied the bottom equation by 2. That means we multiply every term by 2, right? So the system changes. And then what do we do? Add the 2, right? It's not the same system, right? It's not the same one. Is that okay? So this second equation here has these two variables, x1 and x2, right? There are solutions to it, right? X1, and you can solve for the x2. You get two numbers that you can plug in for x1 and x2. It'll solve that equation, right? So does multiplying 2 on both sides, does that change the solutions to that equation? No. So it's a different system, but it has the same solutions. That's what we want. Okay. So this system is not the same system, but whatever is or are, or if it has any at all, it's good, and that hasn't changed because of what we did by multiplying one of those equations by 2. Now, you told me that we're going to add these two together, right? So what happens here? Like these cancel out, right? That's what we wanted to happen. We add these together, we get 5x2, we get 10. Solve for x2. Plug it back in. Which one do you plug it into? Either one. Whatever the solution is to both of them, the x2 coordinate is 2 on both of them. And so the x1 coordinate will be the same on both. So it doesn't matter which one. So I'm going to plug it into the second one. So just replace x2 with 2. Subtract. And I get x1 is 0. So we get 0, 2 as a solution. And a lot of times in this class, instead of xy, we'll call it x1, x2. The x1 is the horizontal component, x2 is the vertical component, but same idea of x and y. Okay. So we multiplied the second one by 2, and that didn't change the solutions, right? And then we added these two together. And we stacked them up like it's a regular numeric addition problem. So why does that work? Why can we do that? I mean, we've always done it, right? Since Algebra 2 or whatever you took in high school, maybe. Why does this work? Why is this okay? It's bad, right? You figure out things that you've just done because somebody told you to, but we need to understand it. Okay, why does it work? Because we want these solutions to be the same. We don't want to mess up with the solutions. So why is it okay to just stack these on top and add them? Say it again? Have the same variables. Well, if I had different variables, I could still add them stacked up like this.
Oh, it's because you eliminated one of the variables?
Well, that's the purpose of doing it, and that's the result that we get. But why is it mathematically correct to do this?
Because it's all addition.
I feel like it's almost my turn. Like if we were to graph the solution.
I'm not, that's not graphing. I'm talking about just stacking them up like this and adding them. I mean, why does that work? Well, here's why, right? Because what is this equal to? It's right. we're adding 6 to this side, and we're adding 6 to this side, right? We're assuming that these equations are true, otherwise, what we're doing is kind of meaningless, right? So if this is always equal to 6, we're adding 6 to this side of this equation, we're adding 6 to this side of the same equation, we're adding 6 to both sides, we're just adding a different version of 6 to the left side. And it's the same if you wrote it out like this. Right? If you just added 6 to both sides, that's equal to 6, and that's equal to 6. Right? You cancel those out and combine those together, you get 5x2. Right? So again, adding one equation to another, as long as you keep the sides on the right sides, right? As long as you stack them up like this and add them that way, it's going to work. Okay? So that's something that we're going to actually do with matrices. So instead of these equations, we're going to have these rows of a matrix. And we want to be able to add them up. We want to be able to add rows together. And we can do that because we already know, you've been taught to do it before. This is why it works, is because you're just adding the same thing to both sides of an equation. Okay? All right. So you do this here, right? So how did this become a 0? Because we multiplied by -3, and we added it to the third row. And these rows are just equations, and this line is like the equation symbol. If the equations stacked up on each other, and we're multiplying this by -3 and adding it to that one, just like we multiplied the second equation by 2, and we added the second equation, or the first equation to it, right? Does that make sense? You're doing the exact same thing. We got more equations here, and we're just dealing with the coefficients because it's going to be easier that way, and we'll have a systematic way to solve these. Okay? Yeah, go ahead.
My next question was, can you do these in a different order and still come up with the same answer? Like tackle different rows and still come up
Yes,
with that? Okay.
but there is a algorithm that will always get you to the reduced form that will solve the system for you. But you can diverge if you see something that will make it easier. You can do that. So that's what we're going to talk about next, is what can you do, and we call them elementary row operations. Okay. So I just wanted to point that out. Is when you were doing this stuff on Monday, it wasn't actually brand new stuff. We're just writing it in a different way, but it works the same way. Okay? So, what are the things that you can do? So what are we allowed to do in order to solve the system without changing the solution set? So what can we do without messing up the solutions? We don't care about changing the system. We want to change the system. We want to simplify it. But we don't want to mess up the solutions. We want our solutions to be the same. So if you forget the matrices for a minute, if we're just dealing with the equations, right, you can replace one equation with the sum of itself and a multiple of another equation. That's what we did on that 2-equation system. We multiplied 1 by 2, added it to another one, we got a new equation. We got that 5x2 equals 10, right? We replaced something. We replaced one equation with another equation that's simpler, right? We eliminated a variable in it. So you can do that, right? And we talked about why. You can swap equations. The order of the equations doesn't matter, right? You can write the equations in whatever order you want. So you can always interchange the order that the equations are in. And you can multiply or divide an equation by a non-zero constant. We did that too. We multiplied an equation by 2, right? And then later we added it. You can do all that in one step, or you can just multiply it by a constant and not add it. Because you can multiply both sides of an equation by a constant, it's not going to change the solutions unless you multiply by 0. Right? If you multiply an equation by 0, it just zeroes everything out. That doesn't help you, right? So it has to be a non-zero constant. So all of these things are allowed. So these are equivalently, I can't say that, they're equivalently called elementary row operations in matrices. So the rows of our matrices can represent equations. So if we're solving a system with matrices, we can do all those same things, but with the rows of a matrix. So I can replace one row by the sum of itself and a multiple of another row. I can multiply a row by a constant and add it to another row, and that's fine. So I'll call that sometimes, add a multiple of one row to another, right? Multiply one row by something and add it to another to try to eliminate variables. You can interchange two rows. So your rows represent equations, and it don't matter what order those equations are in. So you can change rows. You can change the order of the rows. You cannot change the order of the columns. Okay, don't change the columns. And then scaling, you can multiply or divide all entries in a row by a non-zero constant. So you can just multiply a row by a constant or divide it by a constant, and that's not going to change your solutions. All right. And then tips. Only do one of these at a time until you're very comfortable doing this. Okay? When you get comfortable, then you can start doing multiple ones at a time. As long as you understand what you're doing, you can keep track of it. But in the beginning, I don't want you to do that. Okay? I want you to do one at a time. And if you have an error and you want me to check it, it'll be a lot easier to check if I know exactly what you did on each step. Right? I don't have to try to figure it out. So we're going to actually write down what we do each time. That way we can go back and analyze what we did, and if we messed up, we can fix it. And I like to start at the top left and work your way column by column. So you want to start with the top left entry of your matrix. You're going to fix it, and then you're going to fix that column, and you're going to move to the next column. So that's how I do it, unless I see something obvious that I can do to make things easier. Now you can always use any of these row operations. You're not going to mess up the solutions. You can, though, get off on the wrong track, and you can start going in circles, and you'll never get to where you want to go, or it'll take you a lot longer to do that. So there's inefficient ways to solve the systems, right? And if you do too many of the wrong things, then it can take you a long time to get the solutions. But if you follow an algorithm, it'll work every time. And if you happen to see something that you can do to make things easier, then you can do it, as long as you use those 3 row operations. So you can multiply a row by a constant or divide. You can change the order of the rows, and you can multiply or you can add a multiple of one row to another. So as long as you do those 3 things, you do them correctly, you're not going to mess up the solutions, but you may not get any closer to getting the solution. Okay. 2 matrices are called row equivalent if there is a series of row operations that transforms one matrix to the other. So once you do one of these row operations, you change the matrix. 2 matrices are not equal unless they're the same size and they've got the exact same elements in the exact same places. Okay, they have to be exactly the same to be equal. When you change one with a row operation, if you use the row operations that we just talked about and you do it correctly, you don't make any mistakes, then those matrices are row equivalent. And if they're row equivalent, then their systems have the same solution sets. Yeah.
So you wouldn't write them as this matrix equals that other matrix?
No,
So
you do not write equal. Do not use equal sign. Yeah, don't use equal sign. Equals, you get in this habit of writing equals as this is the next step. But that's not what we'll do here, because you don't write two things are equal unless they're equal. Okay, and they won't be the same. And I use a different symbol, and I'll show you what I use when we start solving them. So if two matrices are row equivalent, then the systems that go with them have the same solutions. Right? You're not changing the solutions to the systems. Okay. Two questions about systems that we're always going to be worried about. Is the system consistent? What does consistent means? It means at least one solution. It could be one, or it could be infinitely many, that you can't have two solutions, three solutions, or four solutions. It's always either one or infinitely many. And infinitely many doesn't mean everything. It just means there's infinitely many of them. Okay, they might lie on a line or on a plane, okay, but it won't be everywhere, right? And then the second thing is, if the solution exists, is it the only one? Is it unique? So I think I just said that in one thing. So is there a solution, and is there only one, or is there infinitely many? Okay. So how do you recognize the number of solutions? If you put the system in an augmented matrix and use the elementary row operations to obtain a triangular form, you guys remember triangular form? So the triangular form looks like this. I'll just use a 3 by 3 for example. You get these 3 zeros right here in this triangle below the main diagonal. So the main diagonal will be here. If you got 3 zeros here, you're going to have unique solution. You're going to have one solution. So there will be a solution, there will only be one. And once you get there, right, you could back substitute and figure out what that solution is. So it's always, if you can get it into this triangular form, then you've got a unique solution system. It also works if you make these zeros. So you didn't talk about that, but if you were to kind of do the opposite and do this upper triangle, make that zeros, the same thing will happen. You can start back substituting this way, down instead of up. Yeah?
Does it matter if you have 3 zeros on the bottom, and then what if there's another zero randomly somewhere else? Does that mean?
It doesn't matter. As long as you got those 3 on the bottom, you're good. Yeah. Doesn't matter what else is there. Yeah. Now, this guy can't be a 0. Yeah. But if these are zeros and the main diagonal is not, and maybe, yeah.
Because if that guy were a 0, then the solution would be true.
Right. Yeah. So your goal is to try to get ones along the diagonal, the main diagonal, and zeros below. So what you want to do is what you want is to have ones here, here, and you want to get zeros below. If you can do that, then you got a solution. Then it'll also be easier to substitute once you get those ones. If you have any rows that have all zeros, you need to move those to the bottom. And when you get done, you want to write your system back into its original form with the x's inside. If you get a row of zeros, let's say all 3 of these are 0. Let's do 2 cases here. Let's say I got 2 rows of zeros. if that guy is, say, a 7, what does that mean?
You have a constant of 7.
Yeah.
Yeah, the equation in that should be.
Right, so remember that row represents an equation, right? The vertical line is the equal sign, and the columns are the coefficients of our variables, right? So that row would say 0x1 plus 0x2 plus 0x3 equals 7. And that can't happen, right? So 0 can't equal 7. So if you get all zeros on the left and something non-zero on the right, that is no solution. Yes?
If you get all zeros on the left and a 0 on the right, you don't need to worry about it, right?
That doesn't tell you anything, really. Right now it doesn't. It'll tell us something later. But it might mean we have infinitely many solutions because you reduce the number of equations that you're able to use. So all zeros on the bottom, without this, that might mean infinitely many solutions. Okay, we'll talk about that in a second. It doesn't have to, but if you've got the same number of variables as you have equations and a row of zeros, then it does mean infinitely many solutions. Any questions? So this says if you get values for each variable x1 to xn, then there is a unique solution. So if you get a single value for each variable, then you have a unique solution. So in this example, if we back substitute from here, this is augmented there. It's got the triangular form. It's got the 1s on the main diagonal. It's set up perfectly. We back substitute, we can find the solution. So x3 equals 1, right? So that's what that means right there, right? x3 equals 1. And this says x2 plus x3 equals negative 2. So if that's equal to 1 and I move it over, that negative 2 will become negative 3. You agree with that? I'm plugging it in. I'm back substituting. So that would mean x2 would equal negative 3. And then let's write this one down. So x1 plus 2 times x2 plus 1 times x3 equals 2. We could solve this for x1. So that's negative 6. So negative 6 plus 1 is negative 5. Add 5 to 2, you get 7. So that's why x1 is equal to 7, right? So that's how they got that. So we got a value for each variable. That's a unique solution. We can't get any other solutions. That's it. This is a one-solution problem. Okay. If there are no contradictions, like 0 equals 7, then your system is going to be consistent. But you may not get a single value for each variable. So in this example, it's augmented here. We have this triangular form, but that guy's a 0. See that? So because of that, we have this whole row of zeros. We actually get infinitely many here. So if we write out the system the way it is now and try to solve it, right, the first equation says x1 plus 0x2, I'm not going to write that, plus 13x3 equals 10. Right? And then the second equation says x2 plus 4x3 equals negative 2. So if we look at this, we can see that I've got two equations, but I have three variables. So let's backtrack a little bit. If I have this equation with one variable, I can solve it, right? What do I get? 4? I hope it's 4. All right, so I get one solution, right? I got one equation, one variable. I solve for that variable, I get the solution, right? Well, what if it's like this? One equation with two variables. I have infinite solutions, right? Because the solution now is an ordered pair. There's two values to plug in. And if I plug, whatever x I plug in, I can find a y that'll go with that x. And I can plug in infinitely many different x's, get infinitely many different y's. And you can actually graph these on the line, right? The line is, you put a point on every that forms that solid line, right, that you've always drawn. So if you've got more variables than you have equations, you can get infinitely many solutions. Sometimes you get no solution. So if I have two variables and two equations, right, you can get an intersection where you have one solution, but in this case I have no solution. I've got my y-intercepts at different places, right? So and they have the same slope. So these are parallel lines, right? So this one has no solution, but if I were to change this to say this, then that's going to have. Okay. Remember, if we do the row reduction, the elementary row operations, the solutions don't change. So the solutions to our original system are the same as the solutions to this system. Yes?
So you could, because the third equation is basically saying 0 is equal to 0, right?
Right. So it doesn't really tell us
So
anything.
So you could tell, since there's only, there's three variables, but you know there's only two usable equations, that has infinitely many solutions?
Yes. Yes. So what he said was, if I have three variables, but I only have two equations that are useful, right, that have variables in them, because we reduced this one out, we eliminated this equation, right? This 0 equals 0 equation doesn't help us, right? So because I have two equations, but I have three variables, and you don't have a no solution contradiction, then you have infinitely many solutions, okay? So how do you deal with those infinitely many solutions? Well, I can see that both of these equations depend on x3. See that? So I'm going to solve both of them, one for x1, the other one for x2, and they're both going to be equations in terms of x3. So the solutions are x1, x2, x3, right? They're ordered triples in this case. So I'll write out my solutions, x1, x2, x3. x1, I solve that for x1, so I move this term to the right side, right? So I get negative 13x3 plus 10. And then I move this 4x3 to the right side. I solve for x2 in the second equation. So my x2 is negative 4x3 minus 2. And then the third one, if x1 and x2 are dependent on x3, that means x3 has to be chosen first before I figure out what x1 and x2 are. Does that make sense? So what we do is we call x3 the free variable because we can choose whatever we want for x3. We can choose for x3, and we'll get a solution to the system. And there are infinitely many of them because you can pick infinitely many different x3s. You can pick anything for x3, and it'll give you a solution. So x3 is what we call the free variable. And you always write your system in terms of the free variable if you have them. And sometimes you can have multiple free variables. Yeah.
Is the variable free just because it's in both of the equations?
Yeah. You can tell which one's free by looking at your system that you've reduced, and you've done the best you can as far as getting ones in the diagonal. And I only have these two ones. See that? So we call them leading ones. They're the first non-zero numbers in a row. And this column doesn't have one of those leading ones. So if a column doesn't have a leading one in it, or you can't get one in it, then that's a free variable. So the third column, that's the coefficient of x3, so x3 is our free variable. I can't manipulate this matrix and get a leading one. I could make one of these 1, but I can't make it the first non-zero entry in the rows, whatever row I want to put it in. And then in the third example, we get 0 equals 4, which is a contradiction. So that's a no solution there. Any questions before we move on? This is something that we will use the entire semester. It's this stuff right here that we just did. Okay. Now we might do it a little bit differently later on. By the end of the semester, I'm just going to write down the matrix reduced because I assume that you know how to do it by the end. Okay. But I mean, I'll tell you what I do to reduce them, but I'll just write them down. I'm sorry? Any questions? I thought somebody said something. All right, so let's move on. We're going to solve this system using a matrix. We'll go through the steps. We'll use the same method that you just learned. The next section, I'm going to teach you a different method, but we'll use the same method. We'll get the triangular form, and then we will back substitute, okay, if possible. Okay, so the first thing is we're going to convert it to matrix form. So we put all the coefficients as columns of a matrix. I didn't do that right. So I've already messed up. It's easy to mess these up, okay? That's why we want you to write down what you do. And I like to draw the line saying I've augmented with this other vector. That you can call it the solution vector or the B vector. Sometimes we call it B vector. Okay, so here's where we're going to start. We want to make this top left entry a 1. And we can use those 3 row operations. So I can switch 2 rows, I can multiply by a constant or divide by a constant, and I can multiply a multiple, or I can take a multiple of one row and add it to another. So why don't we just switch the first 2 rows? Okay, so this is the notation that I use. So I'm going to say switch row 1 and row 2, just like that. And then I'm going to rewrite the matrix. And if I mess up, you guys got to help me, okay? There'll be some tedious things with these matrices. Okay, so next, I'm going to well, I want to do the algorithm, but I already say something else I could do. Does anybody say something else? Okay, well, let's do that. That's the algorithm. So we take this 1, and what I call pivoting. You pivot and make that entry, use that 1 to make the entry below it a 0. The way we do that is to take row 2, and we're going to replace it with row 2 minus 3 row 1. See that? So I'm replacing row 2. I'm changing row 2. What am I changing it with? I'm taking a multiple of one row and adding it to the other. So I'm multiplying row 1 by negative 3, and I'm adding it to row 2. Or you could say row 2 minus 3 row 1. So instead of an equal sign, I use tilde to say they're row equivalent. They're row equivalent, they're not the same. They're not equal. So a little tilde symbol. So I'm changing row 2. This is why I like this notation. This is the only thing that's changing. Everything else you write down exactly the way you have it. That's kind of hard for some students to get past, is that you're not really changing row 1. Even though we're multiplying by negative 3 and adding it to row 2, we're just using it to change row 2. And we can do that because we can multiply an equation by negative 3. It's not going to change anything. It's not going to change the solution, sorry. It's not going to change the solutions. And I can add one equation to another because the sides are the same. I'm adding the same thing to both sides. So I'm using row 1 to change row 2. I'm not changing row 1. I want to keep it the same because I want to keep this 1 here, right? I don't want to make that a negative 3. I want to keep it 1, but I'm going to use negative 3 row 1 to change row 2. So let's go through it one at a time. So row 2 minus 3 row 1, and we've got them stacked, right? Stacked up on top of each other, and we're adding a negative 3 times row 1. So 3 and negative 3 is a 0, and that's what I wanted to happen. Right? Everything else is just a byproduct. Right? I did all this just to make that one entry a 0. Negative 1, and that's going to be negative 3. Add them together. Negative 4. Just like that. If you want to write down the two things that you're adding up, that's fine. Okay, go ahead and do that. It's 2, and then we're multiplying that by negative 3. So that's negative 9 and a positive 2. Negative 7. And we're multiplying this by negative 3 and adding it to 5. So negative 30 and 5. Negative 25.
row by 3, and then what's
Negative
the
3,
next- negative 3, and then what's the next step again?
adding it to row 2.
Okay, adding it to row 2.
This right here is what I'm doing. Taking row 2 and I'm subtracting 3 times row 1. That's the negative 3 times row 1. I mean, I could write this the same as negative 3 row 1 plus row 2, like that. Those are the same. Yeah.
I feel like you said it earlier, but your strategy at going at it is you work with the first column first, so you're getting like 1, 0, 0.
Yes. Absolutely.
Why?
Well, we already talked about the triangular form, right? We want that triangular form, and because we're working with row operations and not column operations, if we were doing column operations, you might do it differently, but we're not. We're doing the row operations. And once those are 0, I can make that 1 and use it. And if I make that 1 and I add something to make this a 0, this 0 here is not going to affect that number. Does that make sense? Like, it's just going to make sure that you're doing things efficiently. You don't have to do it that way, though. I'm going to show you in a second. I could have solved this in one step, but we're going to go through the algorithm so you'll know what to do. Okay. So the next step is to pivot again. Use that 1 and make that negative 6 a 0 at the bottom. So how am I going to do that?
R3 plus 6R1.
So I'm changing R3, and I'm going to take R3 and add 6R1. You're correct. Tilde, because they're not equal. They're row equivalent. So that's the symbol we're going to use for row equivalence. And I'm only changing R3, so that means everything else will stay like it is. And I just like to start out that way. Just go ahead and write it down. Only row 3 is going to change. Okay, so one at a time. I'm going to multiply that by 6 and add it to this. I get 0. That's what I wanted to happen. I'm trying to get that triangular form. 6 plus 2. $18 minus 4, right? So 3 times 6 is 18. Minus 4 would be 14. And then 60 plus 3.
So now you're going to take your new R3, and you're going to add 2R2, the new R2 that we got.
You could do that, yes.
Yeah, and then you end up getting a bottom row of 0s and 7.
Okay.
So there's
Wow, convenient, right? So the next step of the algorithm is to make this a 1 and then pivot and make that a 0. But what you're saying is I see that their 2 rows are multiples of each other, right?
Yeah.
So why don't we just use that to our advantage? So what he says, instead of using the algorithm and keep going, let's just multiply one row by 2 and add it to the other one, and it'll 0 out the row. So let's try it. So if we replace row 3, we're going to use the fact that 8 is a multiple of negative 4, right? So if I multiply that by 2 and add it to 8, I'll get 0. So I'm going to say row 3 plus 2 row 2. Again, I'm only changing row 3. So multiplying the second row by 2 and adding it to the third row. So 2 times 0 is 0. 0 plus 0 is 0. So this is a 0. That needs to stay a 0. No matter what you do, you want to keep that triangular form, okay? You don't want to mess up your zeros that you've made. Multiply this by 2, we get negative 8. Plus 8 is 0. Negative 7 times 2 is negative 14. Plus 14 is 0. And then multiply this by 2, you get negative 50, and added to 63. It's 13, right, instead of 7. 13.
So did I make a mistake, or was that the correct answer?
I think it's correct.
I don't like that. I think gets me into trouble.
Well, you tell me, did I make a math error?
No, I don't think so. It's more, did I make a math error?
Well, I would check it again. I would check it again and see. Did you get negative 25 and 63 right here?
I did.
You did? Okay. So we're multiplying that by 2, right?
Yeah. So we're
So
gonna
it'd be negative 50 and 63 is 13.
Yeah. So then so then this solution set it's what?
It's empty.
No solution.
It's no solution, right? So we get all zeros on the left and something that's not 0 on the right. That's a contradiction. This says 0x1 plus 0x2 plus 0x3 equals 13. That can't be true. So this is no solution.
So if you can do that, that's an easy way to see immediately there's no solution.
If two rows are equivalent, or not equivalent, if two rows are multiples of each other, go ahead and add that multiple. It'll zero them out. And then it'll skip a lot of steps. So in the beginning,
So
I should have done that at the beginning.
I was about to say, so really, if you had actually looked at your multiples, you could have been already telling them
Yes.
it wasn't going to have a solution.
Yes. Go ahead.
Well, now I know.
It comes out.
Right? Now I know.
Sorry?
What if it comes out with a solution? Would you still need to make the negative 4 a 1?
Yes. You keep going, yep. If you get 0 here, you make that a 1, and then you do the. Actually, you could go further, but you could find the free variable and write it in terms of the free variable and all that. Yes.
Like you could have, at the very beginning, multiplied the first row by 2 and just got the zeros on the bottom in like one step.
Yeah, that's what we just said, right? If I take the second row, multiply it by 2, and add it to that one,
Oh yeah.
you get it, yeah. The algorithm works every time, okay? You see something that you think will help, skip some steps maybe, then go ahead and try it.
Yeah,
You know-
because, I mean, you're skipping essentially 3 steps there.
Yes. On this problem, yes. Yeah.
And you can always go back and start over.
You know what?
Yes, you can. Yeah. If you try it and it doesn't work, go back to the algorithm. Okay, the algorithm will be your friend. It works here, but if it's a unique solution, you'll have to go through the algorithm to get it. Okay, most likely. Algorithm will be your friend. Yes, we love algorithms. Okay. So we're done with point 1. So that homework's going to be due Wednesday because we're out Monday. It's a holiday, right? So it's due the next time that I see you, but your homeworks will always be due at midnight. So you need to have the homework done, and then anything that you can't figure out, you can ask me on Wednesday. Yeah.
See you Friday. No, we won't. We don't have class
We don't have class Friday. You can come see me Friday.
Friday. I'm sorry. I have my Cal 2 on Friday.
Yeah.
I'm so sorry.
Yeah, we don't have class Friday. This is just Monday, Wednesday class. Okay. So the next section is called row reduction in echelon form. And we introduced matrices here as a way to solve systems of equations. They don't always represent systems. So that's kind of a trap sometimes. You see a matrix, you automatically just want to row reduce it. That's not going to be what we do. That's what we're going to start with, though. Okay. But you could still do row reduction on a matrix, even if it doesn't represent a system. We'll still use that to our advantage to figure things out. Okay, so we're going to kind of talk about row reduction matrices and not necessarily about systems, but we'll relate it back to systems. So a non-zero row or column in a matrix means a row or column that contains at least one non-zero entry. So if a column or a row is a non-zero column, that means it doesn't mean there's no zero entries. It means that there's at least one that's not zero. Okay? Because a zero row or column means they're all zero. That's something that some students will confuse. The opposite of at least one is none. And the opposite of none is at least one. Okay? All and none are not opposites. Okay? So if I say I do not have at least one pet, that means I don't have any, right? Does that make sense? I did not pass at least one of my tests. That means I did not pass any of my tests. I passed 0 of them. Okay? So the opposite, not at least one is none. And not none means at least one. So I didn't fail all of my tests. That means I passed at least one of them. So those are opposites. A leading entry is the leftmost non-zero entry in a row. We call it the leading entry. And most of the times we want that leading entry to be a 1. Leading ones as well. So a rectangular matrix is in echelon form. And this is confusing because I like to call it row echelon form, or REF. That's how it's displayed in your calculator. If you want to find echelon form in your calculator, you use the REF function. Okay? So the row echelon form, it's in row echelon form if it has this property, or all 3 of these properties. Any rows of all zeros are at the bottom. So if you have a row of zeros, you have to switch the rows around until it's at the bottom. Each leading entry of a row is in a column to the right of the leading entry of the row above it. What that means is your leading entries have to be staggered. So this is a leading entry of this row. You see that? It's the leftmost non-zero entry of that row. It has to be to the right of a leading entry that's above it. So this leading entry is here, and what you get is this staggered pattern. Okay? And what's the leading entry in this row? This 5/2, right? It is below and to the right of the one previous. And this is where the word echelon comes in. Echelon is a military term that means staggered. So instead of putting all your troops in a line, you stagger them out. It's called echelon. So we want our leading entries to be an echelon formation so that they're staggered. Yes?
Does that count? Like, since it's not necessarily one over to the right?
So this is not a 1. It is echelon form.
I think mostly what he was saying is
It's not just one.
it's not just 1 over.
It doesn't have to be 1 over.
That's,
Yeah, yeah.
It's the next number.
Doesn't have to be 1 over. And you could have no leading entries in a row. They could all be 0, right? So, but as long they can't be on top of each other, and this one can't be over here.
As long as they are.
So if that's not 0, you have to make it 0, so that the leading entry has to be pushed down the line. Okay. All entries in a column that has a leading 1, that has a leading entry, all the members of that column below that leading entry have to be a 0. So I have a leading entry here. Every other entry below it in the same column has to be 0. Okay? I have a leading entry here. Every entry in that column below that leading entry has to be a 0, so right there. And then this guy doesn't have anything below it, so it doesn't matter for that one. Yes?
So if you had another row, and on another row there was leading entry on the third column, then you would swap that and the third row, right?
Yep, you would make it where it would be right, yes. Where it would follow these properties. You want to do whatever you can to make those happen. Yep. Or you try to make it a 0 if you can. If you can't, yeah. Okay. If a matrix in echelon form, REF, has the following additional conditions, then it's called reduced echelon form or reduced row echelon form, RREF. So RREF is going the extra mile. And you're not just going to eliminate the entries below the leading entries, you're going to eliminate them above as well. So you're going to get that double triangular form. And these leading entries have to be 1. So the leading entry in each non-zero row has to be a 1. So we have these leading entries here. And we eliminate all the entries below the leading ones. We also eliminate all the entries above the leading ones. And if you can do that, it's reduced row echelon form. The book calls it just reduced echelon form, which is not REF. That's RREF. That's what's confusing. So this is not REF in your calculator. That's RREF, reduced row echelon form. So that's confusing, so you got to keep that straight. Just echelon form is what the calculator calls row echelon form. There's actually a column echelon form that you'll never see in your whole life. But the calculator switches between the two. Okay. Why do we like reduced row echelon form?
Because it gives you all your answers to your variables.
Yeah, it does the back substitution step for you. You don't have to back substitute. This equation, if this is a system, we didn't say it was, but if it was, then this says x1 equals 29, and you're done with x1. And the second equation says x2 is 16, we're done. And then the third one says x3 equals 3, and we're done with that one. Okay, and you don't have to do the back substituting step. Yes?
Would this be used in time, or like for the whole process?
It's extra steps in the row reduction and no steps in the back substitution. So whatever you think is easier, but I'm going to make you do that most of the time. Okay, we're actually going to stop back substituting after this section, but if you're just doing it on your own, whatever you think is easier. But the Reduced row echelon form is much nicer to deal with once it's done, but it takes a little bit more work to get it done. So you have to get this lower triangle of zeros and this upper triangle of zeros as well.
And you can write the answer to it as the last vector.
Yeah, well, we're going to write it a lot of different ways, but that's one way to write it. Another way would be as an ordered triple. I went over. I'm sorry. You got to tell me if I go over.